So hello everyone and welcome back. Thanks for showing up today. We have a couple of minutes before class starts. Do you have any questions for me? Okay, good. So the feedback issue, for a moment there I had the volume on the iPad turned on, which might have caused some feedback, but that's off now. There's a question about the last lecture in which we were told that R belongs to this range 1 through B minus 1. Yeah, so in general the modulus, when you take something modulo B, you get something back in the range 0 through B minus 1. We explicitly check for the case B equals 0, so that gives you 1 through B minus 1. And the question is, can't we reduce that to 1 to B minus A? Well, the assumption is that A is larger than B, so B minus A would be a negative number. After today's lecture, the assignment can be completed. Yes. In fact, even before today's lecture, the assignment could be completed, although you will see the particular thing we study today looks sort of similar to one of the assignment questions. So it'll be easier now that you've, after today's lecture. Okay, so the clarification to the question was whether you can reduce that to 1 to A minus B. Well, we know A is bigger than B, but we don't know that it's not much bigger than B. So A minus B in general could be much, much larger than B. And I think probably what you're thinking of is in general, a slow way to do the mod operation is to repeatedly subtract B. So A mod B, the way to do that, one way to do that operation, which is not efficient, is to repeatedly subtract B until you get a number which is smaller than B. And then, right, so the number of times you have to subtract that is A divided by V, the integer version, and then what's left is the remainder, R. But in general, A minus B will give you something that's larger than B minus 1, so it's not the result of the mod operation. Okay, so today's lecture is about one particular algorithm. So now we're really hitting the computer science applications of this stuff, and it's an algorithm for what's probably the classic and most important problem, which is sorting. So you're given a list of things, or an array of things, or a set of things. Doesn't matter what you want to call it. The things can be compared, so for any two things you can say one is less than the other, or vice versa, and you want to output them in sorted order, so in increasing order. So for example, in this, if this is my input list of things in some order, 5, 9, 2, 6, 7, 1, 3, 4, these things happen to be integers. We can definitely compare integers as a natural way, just using the less than relationship. Then the output, so if this is my input for sorting, then the output should be a list of these things in sorted order. So I see 1, 2, 3, 4, 5, 6, 7, and 9. Okay. So that's the sorting problem. Input is something in arbitrary order, output is in sorted order, and sorted order means the first thing is less than the second thing, which is less than the third thing, and so on. And we'll assume that all of the things are distinct, so it's really less than here, not less than or equal to. If they're not distinct, you can just break ties any way you want. Okay. So hopefully the problem statement is clear, and hopefully you've all seen sorting in some application before, or something that you've done before. And the algorithm that we're going to study it's really the classic computer science algorithm, and it's an example of this technique, divide and conquer, which the first times you see it, it kind of looks like magic. And even when you have been studying algorithms for a while, sometimes it even still feels like magic. So you're faced with a problem, you don't know how to solve it necessarily, and so what you do is you break it into two smaller problems, solve those recursively, and then all you're left with is the problem of combining the two solutions to those smaller problems. Okay, so that's what the merge sort algorithm does. So let's try and write some pseudocode for it. So merge sort. It takes a list A, and let's say A is A1, A2, up to AN is a list of integers to sort. Integers, numbers, strings, whatever, anything you can compare, we'll say integers for now. So that's the input, and then the output should be a list L containing A1 through AN, but in sorted order. All right. So, like I said, divide and conquer kind of looks like magic at the beginning, because when you see the way we do this, somehow it looks like we got something for free. So here we go. Let's say L1. We'll make that be the list that contains A1 up through AN over 2. Let's take the floor of n over 2, because if n is odd, we need an integer. And let's say L2 is equal to the floor of n over 2 plus 1 all the way up to AN. Okay. So L1, this is the first half of the list. This is the second half of the list. And now we're going to use the power of recursion and just say actually maybe change this a little bit to make things more consistent. Let's call this one a big A1, this is big A2, and we'll say L1 is equal to the list that we get by sorting this first half of A. So this is A1. L2 is the list that we get by sorting the second half of A. So in this picture here, what this looks like is we get two lists. A1 has 5, 9, 2, 6 in it, and A2 has 7, 1, 3, 4. So this is A1, this is A2. Now we recursively sort A1 and we recursively sort A2. So when we recursively sort A1, we get a list L1, which contains these things in sorted order. So that's 2, 5, 6, and 9. When we recursively sort A2, we get a list L2 that has 1, 3, 4, and 7. And now we want one big list that looks like this, but we don't have that yet. We have this list and we have this list. So let's come up with a function that will take these two lists, and they're both, each one is sorted, and merge them so that we get one big long output list. Okay. And we'll call that function merge, and so it does and then finally, once we've done that, we return L. Okay. So a couple of things missing so far. One of these is obvious. There's a function called merge here, which I haven't defined yet, which is supposed to take two sorted lists, L1 and L2, and return a list containing all the elements of L1 and L2, but in sorted order. But the other thing that some of you maybe noticed is, well, this is a recursive algorithm now. It's calling, right, to call merge sort A, I end up calling merge sort A1 and calling merge sort A2. And recursive algorithms always have an important part of them, the same way that inductive proofs always have an important part, and that's the base case. Okay. So we need to figure out some trivial case, some small case, that it's really easy to sort. Okay. And the trivial case for sorting is, well, it's really easy if somebody gives you an empty list and asks you to sort it. Then the empty list, I mean, there's nothing to sort, so the empty list itself is already sorted. And it's also trivial if someone gives you a list with only one element, then that list is already sorted, right? Because this sorted relation is a relation between pairs of things in your list, consecutive things in your list. And if you only have one thing, well, then there's no pairs. And if you have 0 things, then there's no pairs. So the base case here is just if n is less than or equal to 1, just return A. So if you give me a list that's only has one element in it or no elements in it, then just returning that list works. That's a trivial sort. Already, if n is equal to 2, then there's something you would have to do still, because the 2 elements might be in the wrong order. All right. So that takes care of the base case. And what's left is to define this merge routine. So let's see if we have room for that here. So it's supposed to take two sorted lists and merge them into one long list, L. So let's start with L is equal to, I don't know how you want to write it, maybe a new list, so an empty list. And now let's figure out how to do this. So we have an example here, so we can work with this example. So we've got L1 and L2, and let's say, just to make life easy so we don't have to keep track of indexes, maybe this thing here, we'll call it L1 dot first. So this is L2 dot first. So the first item in the list. And in our sorted list, in our output list, this is in sorted order and this is in sorted order. So the smallest element overall out of everything, so the one that should come first in the output list, L, should be one of these two things, right? Because 2 is smaller than everything else in L1, 1 is smaller than everything else in L2, and so the only question, so that means that one of those two is the smallest overall, and the only question is which one, okay? So we'll have some if statement that is something like, if L1 dot first is smaller than L2 dot first, we should do something. Otherwise, we should do something else. So in this case, L1 dot first is 2, L2 dot first is 1, so we would be in the second case. L1 dot first is not less than L2 dot first. And so what should we do? Well, we should take this element out of L2 and add it to our output list. Okay. So we'll write that here in this code as something like, let's say L2 or L dot append L2 dot remove first. So this looks something like you see in Java with the Java deck interface. Although append is not the term they use in Java. So in this case here, we would want to take the first thing out of L2 and remove it and add it to our empty list L1. And this is now the first thing in L2. And if we do that, if we were going to do that step again, we would be comparing 2 to 3. We would find that L1 dot first is smaller than L2 dot first. So we're up in this case, in which case you should L dot append L2, L1 dot remove first. Okay, so that's the general step. But there's a couple of other sort of things we have to worry about. And here they, what are they? Well, already you can see that if we do this for a while, we'll get into a situation where maybe we run out of elements in one of the lists. Okay, so this already somehow assumes that there is a first element of L1 and there is a first element of L2, but even if they don't start out being empty, well, eventually one of them is going to become empty, and then we should not ask that thing for its first element. So let's do a couple more bits of code here. So let's say L is equal to new list. So we would have something like if L1 is empty, then, so this is L1 is empty, then we should take our new element from L2. If L2 is empty, then we should take our new element from L1. Otherwise, if neither of those two cases, then we know that there is a first thing in L1, there's a first thing in L2. We can compare them and do one of these two steps. And eventually, well, everything is going to become empty. These two lists are both going to become empty, and that means we're done. And so this whole thing should be in a loop that is like this, maybe while L1 is not empty, or L2 is not empty. Okay. And then finally, once that while loop is done, that means we have emptied both L1 and L2. Where did those things go that we removed from L1 and L2? They all ended up in L, so we're done. We've created our sorted list L. We just return L. So here in this example, we start looking at we started looking at 1 and 2. We put 1 there. Now we're looking at 2 and 3. So we'll put the 2 there and remove it from L1. Now we're looking at 5 and 3. So we'll take the 3 and put it in L1. Now we're looking at 4 and 5. So we'll take the 4 and put it in L1. Now we're looking at 5 and 7. So we take the 5 and put it in L1. Now we're looking at 6 and 7. So we take the 6 and put it in L1 in L. And now we're looking at 9 and 7. So we take the 7. And now L2 is empty. So we take whatever the first thing is in L1 and put it here. And now both lists are empty, L1 and L2, so the while loop terminates and we return L. Okay. And indeed, this gives you the correct sorted order. Yeah, so again, this is using the magic of recursion. How did we get these nice sorted lists, L1 and L2? Well, they're just what we get when we recursively sort A1 and we recursively sort A2. If you have the while loop, will it ever hit our if statements? Yes. So the while loop says as long as L1 is not empty or L2 is not empty, you should execute all of these. You should execute this if statement. And the if statements cover all of the the possible cases. If L1 is empty, then we know L2 is not empty. And if L2 is empty, then we know L1 is not empty, so we can take it from there. Otherwise, each one of them, neither of them is empty, so they both have a first element, in which case we compare those first elements to decide whether we take it from L1 or L2. Can I read out the code, please? Sure. To merge L1 and L2, I first create a new list L. And while L1 is not empty, or L2 is not empty, I execute an if statement that has 4 clauses. The first clause checks if L1 is empty, and if so, it removes the first element from L2 and appends it to the list L. The second one checks if L2 is empty, and if so, it removes the first element from L1 and appends it to L. Otherwise, we check if the first element in L1 is smaller than the first element in L2. If so, we take the first element from L1 and we append it to L, and otherwise we take the first element from L2 and append it to L. So exactly what we were doing here when we did this example. The only one of those cases that didn't come up, because they can never both come up in the same execution, is we ran into the case when L2 was empty, so we took the next element from L1. We never ran into the case where L1 was empty and L2 wasn't. But in one run of this thing, you'll never hit both of those cases. Okay, so that's the algorithm, and so what about it? Well, we can sort of try and do a proof that the algorithm is correct, which is not my favorite thing to do, for a couple of reasons, and I'll explain them in a second. But let's see what such a proof would look like. Well, before we do that, let's actually quickly run the algorithm. So let's, just so you understand what's happening in the recursion, let's run this thing on this example. So this thing says we should define A1 and A2. A1 is the first half of the list, and A2 is the second half of the list over there. Guess we can define it now, even though I just erased it. 7, 1, 3, 4. And now we call merge sort on A1. Okay. So we're going to call merge sort on this thing. And what does merge sort do when we call it on A1? Well, it does exactly the same thing again. So it takes the list and splits it into 2 parts. One is the first half, 5 and 9. The other one is the second half, 2 and 6. And then it calls merge sort on the first half. And what does that do? Well, there's 2 elements in the first half, so it's going to split this list into 2 lists. One contains 5, the other one contains 9. And then it calls merge sort on the first half. So it calls it on a list containing only one thing, the number 5. So we fall into the base case, n is less than or equal to 1, and the base case just says return the thing that you, return your input. Okay. So what returns from here is just the list containing 5. Now, in this recursive call, we have just recursively called merge sort to sort the first half of the list. That's this line of code. Now we're going to call it to sort the second half of the list. So it's going to sort this thing, the list containing only 9. That is a list of length 1. So the code, this is the base case. It immediately returns the list containing only 9. At this point, we're at this line of code. So we've got L1, we've got L2. L1 is the list containing 5. L2 is the list containing 9. And now we call merge to merge those two things into a single sorted list. And if we run merge with the arguments L1 and L2, it will happen very quickly. The first thing that will happen is it will compare the first two elements of L1 and L2. The smaller of those two is 5. So 5 will be the first thing to come out. And then the list L1 is going to be empty. So it has to take the next element from L2. And then both lists are empty, so it's done. So the merge is done. It gives the list containing 5, 9, and then it returns that list up to the parent. Now at the parent, we have just finished the recursive call to the first, to sort the first half of the list. So that sorted the first half, the list that contains 5, 9. Now we have to do the recursive call to sort the second half. That recursive call will split it into 2 lists. It will sort the first of those lists recursively, which all that does is immediately return the list because it's only of length 1. Then it will sort the second of those 2 lists, which again is a list of length 1, so it immediately returns. And now that it's got its 2 sorted lists, L1 and L2, it uses the merge algorithm to merge them, which produces the sorted list 2, 6. Okay. So now back up at this level of recursion, we have already called merge to get L1, merge sort to get L1, we've called merge sort to get L2, and now all we have to do is merge those 2 lists. So we need to merge the list 5, 9 with the list 2, 6. And if merge does so correctly, and we think we've checked the code carefully enough, then what comes out of there is 2, 5, 6, 9. Bringing us all the way up to the top level call, in which case, in this top level call, we have just finished sorting the entire first half of the list. Now it's time to sort the second half. And the second half has 4 elements, which are split into 2 lists, each containing 2 elements. The first of those is sorted recursively, which splits it into 2 lists, each containing 1 element. Each of those is sorted trivially, and then they're merged. The list containing 7 and the list containing 1, in this case, are merged to produce the sorted list 1, 7. Now we've just finished sorting the first half of this list. It's time to sort the second half. Which involves splitting the list into 2, then sorting the first half. Sorting the first half is trivial, then sorting the second half, which is also trivial. Then we merge those 2 things into a single sorted list. Now at this level, we have just finished sorting the second half, so we now have the list L1, the sorted first half, the list L2, the sorted second half. We need to merge them using the merge function, and so we get 1, 3, 4, 7. And now we're all the way back at the top of the recursion. We've sorted the first half, we've sorted the second half, and now we need to merge those 2 halves those two sorted halves using the merge function, and we've done actually exactly this exercise already. So what comes out is 1, 2, 3, 4, 5, 6, 7, 9. Okay. So what comes out is the final sorted list in the output. It's not possible to have duplicate values, right? Yes, I said we'll assume that all of the values are distinct. If they're not, then it doesn't really change anything. All that happens is, at least for this code here, if we get duplicate values, then this code prefers to take them from the second list, right? So if we get L1.first is the same as L2.first, then it's not less than, so it would take it from the second list. So it doesn't change anything. I mean, this code still works for duplicate values, but it's easier not to worry about those at this stage. Okay. So, you know, you can try and prove that this thing is correct, and the proof for that would be by induction. And you know, so I'll just sketch it and then explain why I don't really like to do those kinds of proofs. So proof of correctness is by induction on n, the length of the list. The base case so the base cases are n equals 0 or n equals 1, in which case the code just returns the same list you gave it. And so that's, you know, obviously correct. And now the general case. So now assume that the algorithm, don't say the algorithm, let's say merge sort, correctly sorts any list L of length k in the range 0, 1, 2, all the way up to n minus 1. And now prove that it correctly sorts any list of length n. Okay, so then you look at the code and you say, well, okay, by this thing here is the inductive hypothesis that we assume that it correctly sorts any list of length k between 0 and n minus 1. Now, the length of the list A1 is equal to n over 2, the floor of it, right? That's how long this list A1 is. And n over 2 is the floor of n over 2 is less than n, you know, for as long as n is bigger than or equal to 1, in fact. Right? So if n is bigger than or equal to 1, then n over 2 is smaller than n, and the floor of that is smaller still. So this first problem, A1, is a, let me say, correctly sorts any list A. This first list, A1, is has size smaller than n. So by the inductive hypothesis, L1 is a sorted version of A1. Now if I look at A2, how big is that? So it contains the elements whose indices are the floor of n over 2 plus 1 all the way up to n. And if you think about this for a little while, you'll see that what this means is the number of elements in that list is the ceiling of n over 2. And that is less than n as long as n is bigger than or equal to 2. So when n equals 2, 2 over 2 is 1. The ceiling of that is 1, which is smaller than 2. And that works for any n greater than or equal to 2. Doesn't work, though, for n equals 1. Okay. So really, I would say that the only thing that you're checking carefully in this proof is that these conditions here actually get satisfied, because everything else you're going to give off to the inductive hypothesis. So, I mean, you need to check this, that indeed you're recursing on something smaller, and mistakes can be made in implementations here, but this works for any n bigger than or equal to 2. How do we know n is bigger than or equal to 2? Well, if n is less than or equal to 1, then we would have been in the base case. So that's okay. And so by the inductive hypothesis, L2 is a sorted version of A2. And now, well, now you're going to say L is what you get when you merge L1 and L2. And what are you going to do now? Well, maybe write a proof that this merge function is correct. Yes, you can write such a proof using so-called loop invariance. Here we've kind of looked at it and decided that it's correct. And so, you know, so then merge by inspection, or because we prove it, we go through great lengths to prove it. Merge L1, L2 is, so L1 is a sorted version of A1, L2 is a sorted version of A2. A1 followed by A2 is all of A, so that means that this is a sorted version of A. And the result of this, which we call L in the code, that's what gets returned. So this is, I'll put quotes around it, a proof that the result, this algorithm is correct, because what comes back is a sorted version of the original input array A. Okay. Now, why don't I like these kinds of proofs? Well, these proofs of correctness like this, they somehow rely on the code, right? We keep referring back to the code, and it's very easy to say that, well, to make a mistake in that, oh, the code that's actually written here doesn't do exactly what I said it does in the proof. Okay? And so you're just as likely to make a mistake in interpreting the code to do this proof as any mistake that's in the code. So I think these proofs of correctness are useful at a high level, but not for proving that a particular implementation of a particular algorithm is correct, but more for showing at a high level that yes, this algorithm has a correct implementation. And the key steps here are checking the base cases, checking that when you make the recursive calls, that you are actually recursing on something smaller. So that's the sort of non-trivial thing we needed to check here, that floor of n over 2 is smaller than n, and ceiling of n over 2 is smaller than n, as long as we're not in the base case. Yeah, and then arguing that somehow the way you combine those two solutions is also correct. But proving that a bit of code like this is correct is actually a big exercise, and the proof is just as likely to be wrong as the code is likely to be wrong. So I don't put a lot of faith in these things unless you use a real formal proof system where a computer checks the actual proof for you. The computer checks that the code is doing what you think it's doing and that the steps you made in the proof are also correct. Then you can get sort of a real proof of correctness. On the other hand, it's relying on a computer, and whatever code that the computer is using to prove that correctness, you have to believe that that code works too. Okay. Okay. So, but I'm not so interested actually in inductive proof of correctness. What I'm interested in is the running time of this thing. So how fast is this algorithm? So let's So I want to know how fast this thing is, and well, what does that mean? Well, do I mean how fast is it in seconds, minutes, hours, computer instructions? All of those things, those measures are problematic because they depend on the computer that we're using, and so on. So those things are not so useful. So just so that we have something concrete to focus on, what I would like to look at is how many times this if statement executes. Okay. So how many times you evaluate this conditions in this if statement and decide which of the four cases applies. So, and in particular, the thing many people focus on is how many times this thing, this comparison executes. So when people study sorting algorithms, they're often really focused on the number of comparisons performed. So that's the thing that we're going to focus on. And then actually, if you do that, you can convince yourself that everything else that gets done is somehow related to that by a constant factor. So what are all the other things that get done? Well, there's a list A2 that we make here. So, I mean, we have to copy or remove everything from A, the first n over 2 elements, and put them in A1. And then we have to remove the remaining n over 2 elements and put them in A2. If we do that the most trivial way possible, then that's somehow n over 2 steps. We do the recursive call, which doesn't really cost anything. It only takes constant time to make that call. However long that call takes executing is a different story. That we're going to count. And then there's the merge step here. And this merge step, well, it merges the lists L1 and L2. So we have to look at how many times this while loop executes, because that's the running time. And the number of times this while loop executes, that's easy to see. Each time this while loop executes, something gets appended, taken from one of the lists, L1 or L2, and gets added to L, which means that at the end of this process, L, if the original list has length n, then L has length n. So this while loop executes n times. So inside of merge here, there's this while loop that executes n times. And that's what we're counting, how many times it executed. And then there's this thing here, which doesn't, just returning a list doesn't take, it only takes constant time. So all of the other work that's done by the algorithm somehow can be related to how many times this if statement is evaluated, right? N over 2, N over 2, but if these are N over 2 and N over 2, well then this one is actually N. So focusing on this particular thing doesn't mean we're not counting everything else. It just means we're showing that everything else can be bounded in terms of this. Okay. So, so we're going to say, let f of n be the worst case number of times the body of the while loop executes for any input list L of length n. Okay. And actually, this isn't critical. So worst case here just means the maximum number of times it could execute no matter what list you gave me. So even on the worst possible list. In this case, actually, we see that the number of times it executes, certainly at the outer level, was exactly n, right? Because each time it executes, exactly one thing gets added to the output list. But then it gets executed in the recursive calls as well. But the point is that actually the contents of A don't matter. It doesn't change. The contents of A don't change the number of times that this gets executed. All right. So that's good. And let's, for now, make our lives a little bit easier. And we will assume that n is equal to 2 to the k for some integer k. So the example that I showed you that we worked on had 8. It was a list of length 8, so that's 2 to the power 3. And just to make our lives a little bit simpler for now, we'll assume that we're only interested in this function when n is the power of 2. The reason for that is that when n is even, then n over 2 is an integer, and that means the floor of n over 2 and the ceiling of n over 2 is the same thing. And so so that just means that A1 and A2 will always have exactly the same size. They'll always have size n over 2. Okay. So in that case, we know how to define everything now. So let's write a recurrence for f of n. It's a recursive function that we're studying. That recursive function, has a base case and it makes some recursive calls. So we should be able to write this thing that we're studying as a recurrence. And indeed, we can, right? So let's see. There's really only two cases. So if n is less than or equal to 1, then it's something, and otherwise, if n is bigger than or equal to 2. And these two cases, if we're assuming that n is a power of 2, so n is 2 to the k, well, that really means in this case that n equals 1, so k equals 0. And otherwise, if n is bigger than or equal to 2, then what's k? Well, if n equals 2 to the k, then I can take the logarithm of both sides of this equation. So that means log of n is equal to log of 2 to the k. And if you remember, and this is really logarithm base 2, and so if you remember your rules for working with logarithms, the log of a to the power b is b times the log of a. So this thing here is k times log base 2 of 2. And this log base 2 of 2 is a really simple thing, right? Remember, logarithm tells you what power do I have to raise the base to get the argument. And in this case, 2 to the 1 equals 2. So log base 2 of 2 is just 1. So this is just k. So in general, this value k here is just log base 2 of n. And in fact, that's even true when n equals 1. Okay. So, now in the base case, how many times does the while loop inside of merge get executed? Well, the base case returns immediately without calling the merge function at all. So in this case, it's 0. And otherwise, well, all of this stuff happens. So we start out with this list of length n. We recursively sort a list of length of L1, of list of length n over 2, and we recursively sort a list L2 of length n over 2. So that means we're going to have an f of n over 2. That's for sorting L1. We're going to have an f of n over 2. That's for sorting L2. And then we call merge. And merge, we know what it does. This while loop executes n times. Okay. So we get this nice recurrence that perfectly captures the thing that we're studying, the number of executions of the body of the while loop here. Okay. Good. So we would like to figure out what this thing is, and we can do that for a few values of n. So let's do it for if I take n is equal to 1, well then I already have by definition f of n is equal to 0. Now what if n is equal to 2? Well, we can either look at the recurrence or we can look at the code. If we execute the code, that means we start with the list that has two things in it, x and y. We split it into two lists, one that contains x and one that contains y. We recursively sort the first one. That immediately returns, and it does not call the merge function at all. Then we sort the next one. That immediately returns and doesn't call the merge function at all. But now we take the outputs, those two things that were returned to us, and we call the merge function. And so that gives me 2. Okay. The merge function takes two lists, each of length 1, and merges them. That takes 2 steps. Okay. So that's by examining the code here. But we can also look at what the recurrence tells us. It says that f of 2 is equal to f of 1 plus f of 1 plus 2. But this is 0 plus 0 plus 2 is equal to 2. Okay. Now, the next value of n that we're interested in is n equals 4, because we're only going to worry about powers of 2 now. And we can either run the code, which will take a little while, or we can just look at what the recurrence gives us. But f of 4 is equal to f of 2 plus f of 2 plus 4. Now let's make our lives a bit simpler. Let's just write that as 2 times f of 2 plus 4, right? We just have 2 f of 2's here. What's f of 2? Well, f of 2 is f of 1 plus f of 1 plus 4. In fact, we've already done this here. We know that this whole thing, f of 1 plus f of 1 plus 2, and then we have the plus 4 on the outside. In fact, we've already done f of 2. We saw that f of 2 is equal to 2, so, and this is 0, this is 0, and this is 2. So we get 2 times 2 plus 4 is equal to 8. And actually, now that we've seen how to do this, we can do f of 8 really quickly, because f of 8 is going to be f of 4 plus f of 4 plus 8. This is just 2 times f of 4 plus 8, and f of 4 we know is 8. So this is 2 times 8 plus 8 is equal to 20, this is 16, plus 8 is 24. Okay. So f of 1 is 0. f of 2 is 2, f of 4 is 8, and f of 8 is 24. Okay, that's weird looking. For these small things, it's not clear. It's not clear whether this is fast or slow. In fact, we won't know until we can write out some general form. So let's let's take a wild guess. And see if it's correct. Here's the claim. The claim is that f of n is equal to n log base 2 of n. So let's think about that. Does that make sense with what we have? So if this is true, then f of 1 should be equal to 1 times log base 2 of 1. And the logarithm of 1 is 0. So indeed, this is 0. That checks out. If this is true, f of 2 should be equal to 2 times log base 2 of 2. Log base 2 of 2 is 1, so this is just equal to 2. That checks out. F of 3 should be equal to 3 times a log, not f of 3, f of 4 should be equal to 4 times log base 2 of 4. The log base 2 of 4 is 2, right? 2 to the 2 equals 4. So this is 4 times 2 is equal to 8. And indeed, that checks out. And the weird looking one out of all of these was f of 8. Well, that should be equal to 8 times log base 2 of 8. And 8 equals 2 to the power 3. So the log of 8 is equal to 3. So f of 8 should be equal to 8 times 3, which is indeed the 24 that we got. So that checks out. Now, just doing it on a few examples like this does not constitute a proof. It gives us an idea that we're going in the right direction, but we need to do a proof. And the proof is by induction on n. And just to be super clear here, the claim is that f of n is equal to n log base 2 of n when n is equal to 2 to the k, and k bigger than or equal to 0 is an integer. This is only for the case when n is a power of 2. So we'll do this by induction on n, which turns out will also be by induction on k, but let's think of it in terms of n now. So let's try the base case. So the base case is when n is equal to 1 is equal to 2 to the 0. Okay. Well, then we've already seen that f of 1 by definition is 0. And 0 is also equal to 1 times 0. which is also equal to 1 times log base 2 of 1. Okay. So in the case n equals 1, f of n is equal to n log base 2 of n. So that's our base case, all checked out. And now it's time for the inductive step. So inductive hypothesis is that f of, I'm going to have to use a new variable here, r is equal to r log base 2 of r for any r, and well, we're only trying to prove this for powers of 2, so that means for any r in, well, 2 to the 0, 2 to the 1, 2 to the 2, all the way up to 2 to the k minus 1. And now we want to prove for n equals 2 to the k. So we have to be careful about the inductive hypothesis here, because we're trying to prove something that's only true for powers of 2. So that means when we want to assume it for the smaller things, we can only assume it for the smaller things which are a power of 2. We're trying to prove it for n, which is a power of 2, which means we can assume it for smaller values r, but only the ones that are a power of 2, because we're not trying to prove it for the other values, so we can't assume that it's true for those other values. Okay. 2 to the, no, this is up to 2 to the k minus 1, right? So n is 2 to the k. We're going to assume that it's true for any r which is a power of 2 where the exponent in the power is smaller than k. And now it's easy. So prove for n equals 2 to the k, and we only need to do this for k bigger than or equal to 1. We already proved it when k equals 0, so we need to do it for k bigger than or equal to 1. And so what do we have? We have f of n is equal to, apply the definition, because k is bigger than or equal to 1, which means n is bigger than or equal to 2. So that means we get to apply this definition, f of n over 2 plus f of n over 2 plus n. All right. So let's take a look at f of n over 2 here. Well, or let's actually first let's simplify. We have 2 f of n over 2, so let's just write that this way. 2 f of n over 2 plus n. And now we can apply the inductive hypothesis, right? Because here's a value of r, which is a power of 2. What power of 2 is it? It's actually 2 to the k minus 1. If n is 2 to the k, then n over 2 is 2 to the k minus 1. Okay. So this is 2 times f of, well, yeah, I'll leave this as a note. This is 2 to the k minus 1. And this is just a note to say that, yes, indeed I can apply the inductive hypothesis. It's one of those values r for which the inductive hypothesis is true. So let's use that inductive hypothesis. The inductive hypothesis says that this should be r, which is n over 2, log r, so that's log n over 2, plus n. Yeah, plus n. All right. And what's this log of n over 2? Well, for that, we need to remember facts about logs, although it's already showing up from what's on the board. Log of n over 2 is equal to log of n minus log of 2. Okay. So this is just a general fact. Log of a divided by b is equal to the log of a minus the log of b. So that means this thing here, and log of 2 is just 1, so this is log of n minus 1. So let's write this down carefully. We have 2 times n over 2, so those 2's cancel out. So we get an n in front. Log of n over 2 is just log of n minus 1. And let's not forget the plus n, which is multiply the n through n log n minus n plus n, which is just n log n. Let's do a sanity check. Yes, that is what we were trying to prove, that f of n is equal to n log n, and there it is. Okay. All right. So indeed, the number of times the inner body of this while loop executes throughout the entire, all the recursive calls is n log base 2 of n. In fact, it's exactly n log base 2 of n, and that's when n is a power of 2. Okay? So that's how you prove it formally, but here's the way to remember it. So, you know, if you get lost in the sort of math here, there's an easy way to remember this. Which is that when I call this thing on a list of length n, so you draw out the recursion tree, which we've been drawing. When I call this thing on a list of length n, it's going to make its 2 recursive calls, and then it's going to call merge to merge those 2 things. And that last call to merge is going to take n steps. Now what about those 2 recursive calls? Well, those 2 recursive calls behave the same way, but each one of those is on a thing of size n over 2. So this one here, once it's done all its recursion, it will have to do that last merge step, which is going to take n over 2 steps, right? It's outputting a list of length n over 2. Same thing happens on this side. So those 2 recursive calls in their very final step, each one of them will execute that part of the while loop n over 2 times, and this one will execute it n over 2 times. So together, they will execute it n times. But these guys are also recursive functions. Each of these calls merge sort on a list of length n over 4. And the same argument says, well, this is going to have to execute that thing n over 4 times. So is this one, so is this one, so is this one. So there's 4 of them, each of which will do n over 4. So again, that's another n. And this goes on and on and on until, well, at the close to the bottom, you have things of size 2. How many of those things of size 2 do you have? You actually end up with n over 2 of them. And each one executes that thing 2 times. So when I add all these up, I get n. And below that, they're things of size 1, but they don't matter, because they don't execute it at all, right? On subproblems of size 1, you don't do any call to merge. So I have this tree with a bunch of layers, this recursion tree with all these layers. Each layer, I can count it layer by layer, and each layer I get the value number n. Okay? So number of times I spend merging subproblems of size n over 4, that's n. Number of times I spend merging subproblems of size n over 8, that's n. Number of times I spent merging subproblems of size n over 2, that's also n. Okay? So the question is just how many layers does this tree have? Well, this tree is just how many, the depth of this tree, how many layers does it have? It's just how many times can I take n and divide it by 2 until I get the value, 1. Well, that's just, by definition, that's n log n, or that's log n rather. Right. How many times can I take n and divide by 2 before I get the value 1? That's exactly log base 2 of n. So that's the way to remember this thing, is by this recursion tree. But the way to really prove it formally is by this. And if you want to get, if you want to torture yourself, you can try proving this for values of n that are not powers of 2, but you don't get such a beautiful, clear answer. You don't get something that it's exactly equal to this. You get that it's less than or equal to something. And then you have to fight because, yeah, there's a ceiling here and there's a floor here, and you have to do a little bit more work. But it doesn't change the moral of the story. So the whole point is that merge sort runs in O of n log n time. And it does, at most, n log n comparisons. So comparisons means in between comparing two elements in the input. And that's because the while loop that we were counting, it has one of its cases that it gets to that it has to do a comparison between two elements. So if the while loop only executes n log n times, the number of comparisons is not more than n log n. Okay, so that's it for today's lesson. If you have any questions, you can ask me now. Someone asked where n log n came from. It's the guess that I made, well, because I knew the answer. But if you wanted to come up with such a guess, the way to do it would be to draw this this tree, and then you can, start with small examples and then draw this tree. Will there be a review lecture for the midterm? Yes, there will be a lecture before the midterm in which I go over a previous final exam. Not a final exam, a previous midterm exam. Okay. All right, so thanks again for showing up. It's always nice to have some version of a live audience when you're teaching.